Hello viewers, let's look at induction motor. Induction motor, IM. Induction motor is an example of AC machine that converts electrical energy to mechanical energy. And this is using the principle of electromagnetic induction. So we can use just a sketch diagram to explain the concept of induction motor. Let's use this to represent a squirrel cage induction motor. It has some major part, but let's call this starter. Starter. This is a stationary part. It's not moving. We call this rotor. This is rotating part, and this serves as the output terminal. We also have the power supply, and look at three-phase squirrel cage induction motor, and three-phase power supply can come here, supply, and also the rotor sit at what we call bearing. It actually rotates on the bearings. Now we have this thin line between the rotor and the stator. We call that A gap. A gap is the thin line that separates the rotor from the stator. So when the stator coil is energized by an external supply, we will have that it will produce a field, and the field will affect the rotor inductively. So it means that there's an inductive connection between the stator and the rotor. If by any means they are physically connected, that will be a fault. That will be a short circuit fault. So at this point, we also look at two speeds that is noted in induction motor. We have the synchronous speed, that is the speed. We have the synchronous speed. We also have the rotor speed. This is, we write this and we use N on this. So the synchronous speed is influenced by the frequency of the supply, of the supply. Some country will use 50 Hz, while some will use 60. So the synchronous speed is influenced by frequency of the supply, whereas the rotor speed is affected by the load. If at no load, this is going to be this at no load. So when there is load, the rotor current become less than the synchronous current. and that leads us to what we call sleep. Sleep, represented by S. So sleep in induction motor is actually the difference in speed, difference between the synchronous speed and the rotor speed. So at unloads, we always have a sleep that is between 2 to 5%. So it's actually S is ms minus this. So that is the sleep, and we always represent it in percentage. So we can have this, and sleep is equal to this divided by synchronous speed, and you multiply by 100 to make it in percentage. So at this point, we want to represent how the sleep affects the frequency of the rotor. So, but by doing that, we'll also recall this formula um, that the speed is always equal to 120 divided by P multiplied by F, where the F is the frequency and we have P is number of poles of the induction motor. Yes. So at this point, we can also have that the frequency is P divided by 120. So we can also target that the the rotor frequency, we can replace this with this divided by this, and taken from equation 2 where ns is equal to this and this. Replacing this in this, we have that this is equal to P ns divided by 20, we add s. So having seen that, so this is this divided by 120, hence frequency of stator is actually equals to s for the frequency of the line. So please you take note of that. And also we are still on the analysis of the induction motor. Let's look at the rotor side, and we are looking at the rotor side where rotor at standstill. We also look at running condition. So at standstill, we have some of the parameters that we need to analyze. Now at standstill, we can have this to be the voltage of the rotor. We can have this to be the current of the rotor, and this can also be the impedance of the rotor. So looking at current of the rotor, we are using I2 to represent the current, and This will come from Ohm's law divided by the impedance. Of course, this can be further expressed as the square root of this and square root of resistance plus this. We can call this equation. We can call this equation 2. And also, the next is power factor. Power factor is actually the resistance of the rotor divided by the impedance of the rotor. So this is giving us this divided by um, this plus this. So this is your equation 3. So we further express the current. We have seen the current and the power factor. So this comes from this circuit. You can look at this as being the voltage of the rotor. This can give us the resistance and we have the reactance. So this is R2 and X2 and standstill. And also looking at running condition at running condition, and some of the parameters will be affected. Any parameter that depends on frequency will actually be affected. So that is why we are using prime to represent at running condition. Voltage as running condition of the rotor is this and this. As we are multiplying the speed with the standstill value. And also we can put this prime is simply as standstill value. And also this prime is going to be as this. Of course, you can recall that reactant is this, and this. So and frequency is there. Of course, it's also affected. So in this case, at running condition, the current is actually equal to this, to divided by the square root of this plus this, and power factor at running condition is this divided by this plus this and this. So we have equation 4 and we also have equation 5. So at this point we also look at the circuit diagram of, so we can represent this as the voltage, this and also this. So this is going to be this and also this. So this can further be expressed. This can further be expressed as this divided by S and this. So this is the representation of the rotor circuit at running condition. This is running condition. This is running condition. So at this point, we also want to consider a very important parameter, and we call this torque. Torque as a unit is Newton meter. This is the horizontal force that causes the rotation of the rotor. And we also need to clarify torque under two conditions: torque under standstill, and also under running condition. So at this point, let's see how we can analyze this. Let's see how we can analyze this. That torque depends on one, the rotor current, that is this. Torque also depends on power factor of the rotor, and also finally the voltage of the rotor. Um, this is cos this, and also this is this. Here's the angle between the current and the voltage. So from these three conditions, we can have that standstill or starting torque is actually um, directly proportional to the, this, this, and this. This is the voltage, the current, and the power factor. So at this point, we can remove the sign and write this. So when we are doing that, we can also replace this and this with the original formula that we've gotten. That is the power factor and the current. So we have that starting torque is actually equals to, we maintain this. This is this divided by um, resistance and reactance. And also this is resistance divided by the impedance. This is this. This is this is this and that. So when we want to simplify this expression, we are having that this is equals to this, and this is this divided by this, and this cancel out the square root. We're having this plus this. So at this point, we can actually say that the starting torque is 3 divided by this. This is multiply the whole of this with this. So this is starting torque when this represents the constant. Okay. So we want to analyze some of the conditions you can achieve maximum starting torque. Maximum starting torque. So at this point, we want to consider how we can have maximum starting torque. So we can repeat this K1. This will take place, will take care of that. After all, voltage is constant in this case. So 3 this taking replaced by K1, and we divide this by this plus this. So at this point, let's differentiate this relationship with respect to the resistance of the rotor. So while doing that, we are having ds d r2 is going to give us that this, and this, multiply with the division of this will give you K1 minus K1 R2 into 2 R this. All of this divided by this raised to power of 2. So when we try to simplify this expression, we are having K1 R this plus K1 this times this is giving us minus 2 K1 R this and this. So all this you divide with this. So at this point when we work on this and this the same, so we can write this out minus this will give us just one of them. So we have K1 out this divided by this. So in having a point, a stationary point, the TS divided by the R2 will be equal to 0. So let's figure out how we can analyze this. So we are having that K1 out this minus K1 R is equal to 0. So this is equal to this K1, this is K1, sorry, and equal to this. So this will cancel out. We are having this equals to this. So finding square root of both sides. So this is giving us that this is this. So hence for maximum starting torque, the rotor reactant must also be the same as rotor resistance. This will also be the same to this. So that is a condition. So if you are going back to the original equation, we are having that starting torque is going to be mk this in place of R2 put x2. So this is going to be x2 plus this is x2. So we are having that and you can put this as even k1, which is this, into 2. Yes. So this will give us that starting torque is only concerned, this is this, divided by 2 this. So that is the maximum starting torque. Also on this similar vein, let's look at running torque. Torque of induction motor running condition. So at this point, as earlier said, that some of the parameters will be affected. So we're having that the running, we can use this to represent the voltage. Yes, the voltage. This will give us, and this will give us the power factor. So if we remove this, you can have this cross the that this is theta, this is theta. So we can actually replace the current with S, that is for running condition, plus as for running condition. We also have this, that is for power factor. So this is giving us here this divided by this squared, that represents a running torque, which we can further express as keeping this as constant and put it K1, and this will replace this, and we have this divided by this plus this squared and that. So let's look at the condition for maximum running torque. Condition for maximum running torque. We can achieve that by differentiating this with respect to slip. With respect to slip, so this will give us that we differentiate this one with respect to S. So we have the denominator being multiplied. We differentiate this, so that will give us this out minus. We write this out, this, and we differentiate this with respect to S. This is 0 and this is 2S. This, all of this raised to the power of this plus this. So at this point we can actually simplify this expression, and the TR divided by the S is giving us as we this reply with this, we have K1 R2 raised to the power of 3, and this times this, we have plus K1, we have S, we have this squared, and we have this. Multiplying this to this, we have 2 K1 S squared. So this, and that. So divide the whole thing by okay. So this will give us K1 R2 to the power of 3 minus K1 R2 this and that divided by this, all this power of 2. In looking at the stationary points, we have to equate this to 0. So this and this is equal to 0. And hence we have in this equals to 0. So taking this to the other side, we can have K1 this into this, that. So we can factorize out this. So this will cancel out and this will cancel. So we're having this squared equals to this squared. So taking the square root of both sides, we have s this equals to half this. So s is actually equals to this divided by x. So for a maximum running torque, we are having that the rotor resistance must be this for a maximum running torque. So this is the condition that for a maximum running torque, the rotor resistance must be slip multiplied with the rotor reactance. So at this point, we are going to stop here for further examples on our subsequent videos on this topic. Let's look forward to other exciting topics. From what we've done so far on the analysis, we can try our hands on this assignment. We have three assignments here. One is a 50 Hz 4 poles and 3 phase induction motor has a rotor current of frequency 2 Hz. Determine the slip and also the speed of the motor. The second one is a 50 Hz 8 pole 3 phase induction motor runs with the speed of 50 rps. Find the slip and the synchronous speed. Finally, we have the rotor of an induction motor has a frequency of 3.5 Hz. Find the slip if the motor has 8 poles with line frequency of 50 Hz. Please write the answer on the comment section.